All right. Absolute value parent functions. Here we go. So every function has a parent function. And what that is, let's highlight for fun, the parent function. It is the most basic form of a function. No transformations. It is in its most simple, simplistic, we'll say, form. Okay. So, sorry, for the absolute value function, in parent function form, notice h and k are 0 and a is 1. That or those attributes hold true to every function in parent function form. Okay, so since h and k are 0, and we don't really need to create this x and y chart for this function, but we will for the future ones, and so I'm just going to do it to get us into the habit. Since h and k are 0, that's our vertex, and then I'll use -1, -2, 1, and 2, and plug them into the function to get their corresponding y values. Okay, so then -1 absolute value is 1, and you'll notice that it is the same on either side of the vertex, the same y values. So let's graph it. We have a vertex at 0, 0, up 1 over 1. Yes, you can absolutely use the a value to graph as a slope, but keep in mind that this is the only function where I will allow you, without getting a little bit perturbed, no, this is really the only function that the a value is the slope. Every other function we see is either growing exponentially, decreasing exponentially. It's not a constant rate of change between one point to the next. This is also a symmetrical function, which is kind of neat. So the left side can be reflected across this axis of symmetry. And the axis of symmetry is a dashed line. It's a characteristic of the function. It is not the function. It cuts straight through the vertex. So our axis of symmetry is always in the form x equals h. It's a vertical line, so it's x equals, and it shares, pardon me, the x coordinate of the vertex, or the h. All right, so there's our parent function for the absolute value. We have a bunch of characteristics that we need to address for every function. We need to be able to identify them, talk about them, describe them. So the first one is the vertex, or in our hk, so 0, 0. Since there aren't any shifts, the x and y intercepts are 0, 0. And please make a note somewhere that these are coordinates. Intercepts are locations on a graph. They have an x and a y value. We don't just want to say, oh, x-intercept 2. Well, it might have an x value of 2, but we have to note that it is at 2, 0. It's on the x-axis. Okay. Domain. The domain represents all of the x values that exist on or in this function. And this one is all real numbers because there aren't any restrictions. There aren't any x values that don't have corresponding y values. If we wanted to write it in interval notation, we would say that it goes from -infinity to +infinity, non-inclusive, because infinity is a concept. Right? We can go to infinity and beyond in theory, but we can't ever get there. Range, just like domain, should always be discussed from smallest to largest. Since this function opens up, we start at the k value of the vertex. We say that it starts at 0, inclusive, and goes to infinity. If you're more comfortable in set notation right now, we would say that y is greater than or equal to 0. Okay, increasing and decreasing intervals. For most of us, these are new. Okay, these are going to be discussed with the domain elements. Okay, we talk about these with x values. And they're intervals of space. We say that from this x value to that x value, our y values increase. So if we look at our graph, right, and you don't have to highlight, but I'm going to for us. We read a book from left to right. So we read a graph from left to right. As my highlighter goes from left to right, notice that my y values are decreasing. My highlighter is going down. That means that my graph is decreasing from -infinity to 0. Okay, at the vertex, I'm switching direction. And then from 0 to infinity, my y values increase. So our increasing interval is 0 to infinity. In other words, as x goes from 0 to infinity, my y values increase. Okay, now those might be a little bit challenging for you as far as conceptually, but don't worry, we're going to be talking about it a lot, and we're going to be practicing a lot. So you'll get practice with it for redundancy, sorry. Okay, is the function 1 to 1? Well, looking at this, the definition of a 1-to-1 function is for every x value, there is one and only one corresponding y value. And for every y value, there is one and only one corresponding x value. Man, how do we even say that or see it? Well, we test functionality with the vertical line test, right? If my pencil is vertical, so let's take the orange, right? If I draw a vertical line, I only touch the graph in one spot. True. Okay, see if I can erase it without erasing the function. All right. Well, if I'm 1-to-1, you're not only passing the vertical line test, you're passing the horizontal line test as well. So I'm just going to pick a random spot and draw a vertical line because you can't see my pen at the moment. I intersect the graph at not 1, but 2 points at the same time. Since that occurs at all, our function is not 1-to-1. Okay, so again, for 1-to-1 function, you have to pass the vertical and the horizontal line test. Okay. Rate of change, our slope is 1, but I want to address not only the left and the right, so we're going to put plus and minus 1. We already talked about the axis of symmetry being the h value, so x is equal to 0. Don't forget to write down x equals, because it is a line even though it's dashed. And then minimum and maximum values. These have to be addressed with the range. Okay, so it is actually the y value of your vertex, and you just have to figure out, is there a maximum or a minimum value? Well, since this graph opens up, we go up to positive infinity, there's a minimum value of 0. All right, so we're going to put minimum value 0. The maximum does not apply to our function. And we have one left, asymptotes. Yeah, we don't know what those are yet. So we put NA for those two characteristics. All right, so there is our absolute value function in parent function form. Okay, so let's look at now our second example. And above it, you'll notice that this is the generic equation for an absolute value where we've got A, H, and K. And this is a perfect example, or I should say display, of why we take the opposite sign for every h value. In the equation, it's x minus h, right? Well, if h is -2 and we substitute it in, now we get the absolute value of x plus 2. That, ladies and gentlemen, is why we take the opposite sign of our h value. Okay, for this example, we can see that a, which is in front of the absolute value bars, is -2/3. We need to remember that it's a -1 times 2/3. And the reason why that's so important is with our transformation language. We get the vertical reflection, which means it's going to open down because there's a -1 being multiplied. We then get, since a is between 0 and 1, 2/3 is between 0 and 1, it's going to be a vertical compression. So it's going to be a wider absolute value, which makes sense thinking about 2/3 as a slope. We can see that h is 2, which means we're going to go 2 units to the right. H is our horizontal, remember? Our horizontal translation. And k is 6, so we're going to go 6 units up. Sweet, let's graph it. We know that HK is 2, 6, so that is our vertex 1, 2, 3, 4, 5, 6. And then I'm going to go down 2 and over 1, 2, 3 to the right, and down 2 and over 1, 2, 3 to the left. Do it again, 1, 2, 3. So yes, please try to give me a minimum of 5 points so that we get a nice representation of what the function looks like. All right, let's do the characteristics, ladies and gents. HK, we already discussed that. It is 2, 6, which means we know that the axis of symmetry is going to be x equals 2. You don't necessarily have to sketch it in. You can if you would like, but we do need to be able to acknowledge it exists and state the location of where it is. Now, x and y intercepts, gosh, I could look and guess, but I need to be exact. So we'll come back to that in a second. The domain is, again, all real numbers. There are no restrictions on the domain, or negative infinity to positive infinity. Restrictions on the domain might be if there is a fraction, right? The denominator can't be 0. Excuse me, that would be a restriction on the domain. Okay, range. Smallest to largest, we are going to go from negative infinity, because this is pointing down, up to the k value. So we're going to go from negative infinity to 6 inclusive. It's a closed circle. Or if you want to do set notation, y is less than or equal to negative 6. Definitely not negative 6. 6. Increasing and decreasing intervals. As we look at our function from left to right, our y values are increasing from negative infinity to x equals 2. So we're going to say the increasing interval is from negative infinity to positive 2. And therefore, it's from x equals 2 to infinity, the y values are decreasing. This is not one-to-one because just like the parent function, this absolute value function doesn't pass the horizontal line test, and the rate of change is plus and minus 2/3. Since it opens down, we have a maximum value, and that's always the y value, the k, and the minimum doesn't apply, and our asymptotes don't exist yet because we don't know what they are. But they're gonna come in, I think, Unit 4. Something to look forward to. You're welcome. Okay, x and y intercepts. Yes, we can guesstimate, but we need to be exact. So, in order to find a y-intercept algebraically, we need to take 0 and substitute it in for y because I'm on the y-axis. I'm not shifting left or right. Okay, if you need to write that down on your notes, please do. Y is equal to negative 2/3 times the absolute value of 0 minus 2 plus 6. Keep going. Negative 2/3. Inside the absolute value bar is 0 minus 2 is negative 2 plus 6. Absolute value represents the distance that a number is from 0 on the number line. So if I'm the absolute value of 2, distance is always positive, so it's 2 plus 6. Keep going. Multiply fractions, so 2/3 times 2, still keep the negative. We get a negative 4/3 plus 6. I'd like to get common denominators, so that 6 becomes 18/3, and our y-intercept is at 14/3. You can always go back and check on the graph, and yeah, it looks like it definitely correlates. Well done. But we need to write it as a coordinate. You can, if you would like, put it into mixed number format, or you can keep it as an improper fraction. What we can't do is write it as an approximated decimal, because then I'm not the exact value, and that's not at all what I was asked to find. Okie dokie. Here we go. Grand finale, x-intercept. Do the opposite. Take 0 and substitute it in for y, because we are on the x-axis, so I don't move up or down. Okay, in order to solve an absolute value equation, you need to isolate the absolute value bars. So I'm going to subtract 6 to both sides. So negative 6 is equal to negative 2/3 times the absolute value of x minus 2. In order to get rid of that fraction that's being multiplied on the right side of the equation, I'm going to multiply both sides by its reciprocal. Okay, so be careful. We're not multiplying by the opposite reciprocal. That only comes into play when we're dealing with perpendicular slopes for lines. Okay, so when we multiply that, we get that these will cancel, and we get the absolute value of x minus 2 equal to negative 6 times negative 3/2. Well, negative 6 times negative 3/2 gives us 18/2, multiply across, which is 9. And remember, The absolute value represents the distance that a number is from 0. So if I tell you that the absolute value of x is 4, we'll say, and I ask you what is x, you think to yourself, well, shoot, 4 and -4 are 4 units away from 0, so those are my two answers. It's at this point in the solving process that we need to think of that as well. The quantity inside, x minus 2, it could be 9, but it could also be -9 because both are 9 units away from 0. And then we solve. So adding 2 to both sides, x is 11 and x is -7. And then last but not least, we need to write it as coordinates. So we get 11, 0 and -7, 0. Doesn't matter which one you write first to me. What matters is that they're written as coordinates. And we're done. Excellent.